Great. Yeah. So just start. This part is just about how to run the detailed steps in DESeq. So DESeq models the counts of each data by negative binomial distribution, and I is one gene, J is one sample, sigma mu is the mean, sigma is the variance, and they may assume that for the samples of the same sample group are with the same sigma. So once you do the test, you just regard all the samples are with the same. For one gene, all the samples are with the same mu or same sigma, but you only need some adjustment there. Because the observed data for each, the observed counts are biased by the total counts, total number of counts. Just like the idea we do the RPKM, we may need to adjust it. So here, for mu ij, it is modeled by Qi and the rho j. Rho j is that means all the conditions. Rho j equal to all the samples j with the same condition are with the same value here. So that means we just give a Q of gene I and for all the samples of the same condition. And Sj means just a value represent the average expression level or the total expression level of the count of each sample. So here we can say S is an adjustment parameter that are necessary for DESeq, but S can be the total expression value, total counts. S can also be the median expression, the median counts. So it depends on your definition. S can be just you can define it. But what they did, they define S is here. It's just if the first do adjustment of each counts for each gene I, and for the they just here you can see the Kij is Kij divided by a value. The value is the geometric mean of the genes in each sample, and Sj is defined by this value. So we can see, then I will plot. I will see what is the S looks like, and how S is different to the total counts and to the median. So here we go. Still 6. Yeah, just do it this way. So still 6 samples, and sample 1, sample 2, sample 3, and also the of first diet, and sample 4, sample 5, sample 6 for the second diet. And this is the total counts. This is the median counts, the median value of the counts in each sample. This is S. So you can say S is not the same as the total counts. So what this plot can tell us. So the total counts are quite the same of all the conditions, but the median counts are quite different. So what does it suggest? Suggests that, so for this condition, so the median value is still very high. That means that with relatively more genes are with a moderate or high expression. But for this condition, the median value is quite low. That means this condition may have some genes with extremely high expression, or very high expression, or small proportion of genes are with high expression, but the rest are more, compared to the second condition, there are more genes are with relatively lower expression. But please keep in mind, the constant is also a relative value, not exact gene expression. That means probably the most reliable explanation is that in this condition, more genes are expressed, and this condition, less genes are expressed, so like that. But as you can see, S can be very different compared to counts. So here, this assumption is, I should say, is robuster comparing to this one and comparing to median. But how robust it is, you can test. But you can see, if we change the definition of S, this tuning parameter will be, or adjusting parameters will be changed a lot. This formula will, this formula will change a lot. So, and definitely affect the final result. So this is the first thing that is may not be that robust for DESeq. With changing S, you may get totally different result, or changing different definition of S. So sometimes if the DESeq you get DESeq for, no one will publish result by DESeq, by just DESeq analysis. Because once you get the RNA-Seq data analysis done for 3-to-3 comparisons, you may need to go downstream pathway level analysis, or you need, for certain genes, you may need PCR validation. If you have done those, you'll be okay. But if you just find the first step, differential expression tests are with something wrong there. Think about check about the data, the shape of the data for each sample, and think about if S is problematic. And you can run similar procedure by changing S. This is the first problem. And then we fit we just use this S. And we fit the sigma and fit the mu of each by using the DESeq procedure. This is provided here. It's like Q is provided by, it can be estimated by this procedure. And they introduce some parameters like W and Z. We can ignore this part, but these are good for estimate the mu and the sigma. So basically what we do here is we just follow the procedure provided by this paper, and to ask and regard these two. First, we think we do two fitting. We do 4 fittings. First, for the cons data we do 2 fittings. First, we consider the 2 conditions as 2 different conditions, and we fit negative binomial distributions by using the cons, and for each of the sample, for each of the condition and of this gene. And also, we regard the 6 samples as 1 population, and we fit another negative binomial distribution. I want to let you see, okay, what we can get through the procedure. And also, we fit the RPKM value of these genes, of the 2 conditions. First, because these genes, the expression are high enough, we just use log RPKM and regard, just assume they may follow after the take log of RPKM, they may follow a normal distribution, and still fit the 2 conditions as fit the 6 samples as 2 different conditions and 1 same condition. How to get this? Here, we just do the fitting, and the fitting can be very fast. It's just do one for 1 gene, and we do fitting with this procedure. It's just some basic calculation to fit the sigma and mu, and with different assumption. So this is the first plot I want to see. So yeah, here we go. So this is the results of negative binomial fitting. The red one is for the pink, the light pink one is for the first condition, first diet. The blue one is for the second diet. And once after fit the data by the parameters of negative binomial distribution for each of the conditions, by treating the 2 conditions as 2 different populations, after we get the parameter, we randomly sample 1,000 random numbers from that distribution to plot, okay, what the shapes of the distribution, the fitted distribution looks like. This is a binomial case, and this is the normal case for the log RPKM. So the first thing I want you to understand is that, so DESeq, it involves a negative binomial distribution is still very strong. It's also very strong, because sometimes people may think, okay, how can I fit a normal distribution just by 3 points? The same way happens there. How can I fit 3 points, fit a negative binomial distribution by 3 points? So I think you can remember the gene expression value of the gene is like 0, or just plot it again. Just print it again. So gene expression level, the counts of these genes. It's 1 to 8 from the first condition. And the first condition here is 15 actually. 1 to 8 is here. So this the first fitting is okay. The first fitting because the gene expression level is okay, looks like okay. But the second one you have is 75, 47, 41. So you get 75 here, 47 here, 41 here. It's kind of, you just get the 3 values there and you get the whole distribution. This can be not problematic, but this can be not that robust. So just imagine if you change 141 just to 20, or just you change 75 to 95, how much you will change the result. And also this kind of, but here just want to get your general point, general idea that okay, DESeq still has the problem that we're still using very small amount of data point to fit distribution. This is always a problem. And for some statistical background students, you may know, okay, how to test the robustness. We just simulate to distribution and use some bootstrapping ways to see how robust this can be. But the general point for the non-statistical background students you get is that we're still using a very small number of samples to fit the data. So this can be also with a big false discovery rate possibility. But another point here I want to conduct here is that you can see the 2 normal distributions, the overlap is this level, but the 2 negative binomial distributions, the overlap is this level. So we'll compute the area and you try to do some probability-based test, you do some random sampling type-based test, you may say, okay, the power, the sensitivity of this one may be even higher than this one, or the p-value of this one may be even smaller than this one. So, but it depends on how rational of the t-test is. So for this case, t-test is maybe more sensitive, but for some low expression level cases, t-test is not that good. So, but at least here you can see the fitting here of negative binomial for low expression level, it looks good. But for high expression level, it's not that good. But for t-test, high expression, probably because we really think that we really can derive that if the RBChem expression level are high, we can empirically derive or theoretically derive if we in the same population, the error of RBChem of the same condition is follows a normal distribution after you take log of the RBChem. So this is my personal thinking is that, so for the high expression case, t-test may be okay. For low expression case, negative binomial will be better. So you can get this kind of this idea. But definitely, if you want to make this clear, you need to do more simulation or more testing. What I want to say talk about here is that like still all models are wrong, but you can use some simulation or just split the steps, get into the methods, how it works to see, okay, how the models how the models work and get some insight about, okay, which data it works better, in which cases it works better, which is not. And here is just another distribution. It's like we consider them as a whole, just consider 2 conditions as the same distribution. And this is the null hypothesis we use for a test. For t-test, it's like this one. The null hypothesis, we just consider it as the total normal, and the null hypothesis for the negative binomial we have hypothesis is this is for all the 6 samples from the 1 negative binomial distribution. And we can see this value is 200. It's no longer 50. So 50 may be just around here. So, and with this assumption and with this big variance, there are also possibility to get really high counts and of this distribution. But in more cases, maybe like 0 or very small values. So still, this one may not be that rational, but please keep in mind, this is just the hypothesis, the null distribution. It's not that important to evaluate the model's correctness or the robustness. But with this distribution, and with this distribution, and with the adjusted value there, we can use probability or something like that to compute the significance, just as what we do for a permutation test. Similar to that, but definitely we can get an empirical distribution, the p-value. So these are all about the hands-on part. So let's take a 5 minutes break.